Hello, my name is Kostas Pirgakis and I'm going to present you a work with the title A Cross-Interval Transshipment Model to Optimize Power Cogeneration. And this work draws incentives from real-life design problems of multiple product biorefineries. So in this presentation we are going to discuss about the background for the implementation of integration cogeneration analysis, while next we are going to discuss about summarizing challenges in the field of biorefineries design. Next, we are going to present two methodologies. The first refers to coupling different stages of integration procedure as a single integration tool, while in the second case, we are going to revisit some conventional strategies for the approximation of cogeneration potential. And this presentation closes with a case study where the methodologies are applied. So this is a general scheme that includes the general heat flows of a multiple process plant where water is boiled for the production of very high pressure steam, which is expanding into a complex steam turbine for the generation of shaft work as well as for the generation of the intermediate utility levels, through which heat is provided to each individual process, while the process at the same time are capable to exchange steam by offering heat and the generation of steam at the intermediate utility levels. So, cogeneration analysis is implemented as a post-energy integration analysis, where at the first step, direct integration is implemented inside each process involved in the multiple process plant. So in a process with a given number of hot and cold streams, heat cascade technologies are naturally used in order to estimate the maximum feasible heat recovery among the streams, while heat transshipment technologies are used to debottleneck the heat cascades and result with the grand composite curves of each individual process involved in the multiple process plant. At next, indirect integration is implemented among the processes of the plant, where excess heat of a process is used for the generation of steam, which can be used by another process replacing fresh steam demands. And these steam savings can be graphically previewed through the side sources and sinks profiles, which actually combines the individual lines of the grand composite curves of each process. Finally, by horizontally shifting the curves of the side sources and sinks profile, we can graphically preview the maximum feasible heat that can be used for cogeneration purposes. So in the case of biorefineries, we have to address candidate, competitive and existing processes that can be combined in different ways, and they can exchange mass and energy flows through different biorefinery scenarios, each of which features with different efficiencies. So the case here is to investigate all these potential synergies in a systematic way among the candidate and existing process in order to reveal promising biorefinery solutions of high efficiencies. So under these conditions, the processes in the integration procedure constitute additional degrees of freedom, and since the processes and their heat demands are not known beforehand, we cannot directly implement the step-by-step integration and cogeneration analysis for design of the steam turbine system. So the biorefinery value chain problem looks like this, where excess heat of candidate processes can be used for the generation of steam, which along with fresh generated steam can be used through the steam turbines for the cogeneration of shaft work and electricity, which actually constitutes an additional biorefinery product, which is not visible in value chains, but is still necessary in order to offset price volatilities of the upcoming chemicals. To address the combinatorial process synthesis and integration problem, let us use this representation, which includes the heat cascades of all individual processes included into the value chain, where each cascade is responsible for the direct integration of within each process, while the different processes are indirectly integrated through the central utility system. In order to couple direct and indirect integration of hot and cold streams, either they belong to the same process or different process, the integration concept assumes that all intervals of all candidate heat cascades are incorporated along a single cascade called total site cascade, where all hot and cold streams of all candidate processes contribute, and they can appropriately, directly and indirectly get integrated following some specific rules. So the total site cascade works like this. Let's say that we have a hot and a cold stream that both belong to the same process. Then heat flows along the total site cascade are still working for direct integration purposes. Now let's say that we have a third cold stream that belongs to another process. Then available heat from process A is extracted via external heat flows outside the total site cascade, and this heat is transferred to the utility level, where the heat is translated into steam, and finally the steam is transferred to the corresponding interval where the cold stream of process B is applied. Now, after having completed direct and indirect integration along the total site cascade, finally we can estimate the minimum fresh steam demands that close the overall energy balance. So in order to systematically describe the above procedure, we took a conventional heat transshipment model that has been exclusively used for direct integration purposes. So we updated the model with additional energy nodes and energy flows in order to embed the indirect integration into the conventional concept. So the heat flow that connects nodes 1 to 3 still works for direct integration purposes, while at the same time, in order to prevent direct integration between hot and cold streams that belong to different processes, we can easily block the respective flows. In addition, we added nodes 4 and 5, where through node 4 we can extract heat from the interval, and there the heat is translated into steam, and this steam is next transferred to node 5, where the steam utilities are applied. Finally, in the case that we have excess of generated steam, we are using steam residuals to cascade this steam to lower temperature utility levels. So this transshipment model that is capable to connect intervals at different temperature is finally called as a cross-interval transshipment. At first, the energy bridges that connect nodes 4 to 5 can be used in order to describe the steam savings due to indirect integration, while node 4 represents its utility level where heat is extracted for steam generation purposes. At third, steam residuals that cascade steam among consecutive utility levels can be used in order to approximate the cogeneration potential due to expansion of steam between consecutive utility levels that form an expansion zone. For the approximation of the power output of a steam turbine, the turbine-hardened model has been extensively used in order to face non-linearities between the isentropic efficiency and the steam load. So the model is based on the experimental results of Peterson and Mann, which can be reformulated in that way in order to develop piecewise linear approximations that, if appropriately combined with the isentropic efficiency expression, there can be concluded to the simplified equation of turbine-hardened model, where power output can be estimated with a linear expression that is using the steam load. The turbine-hardened model can be applied for a steam turbine with a single input and a single output. When the turbine-hardened model is intended to address biorefinery cases where infinite energy profiles are generated by combining candidate value chain processes, it is important to use a dense grid of candidate utility levels into the entire temperature range from the higher to the lower temperature that is present into the value chain in order to appropriately investigate for excess heat of processes across the entire range and accordingly improve steam savings and cogeneration at the same time. So for the implementation of the turbine-hardened model, the user has to prepare the regression parameters A and B that are based on an operating parameter phi of a steam turbine, as well as he has to prepare the isentropic enthalpy change, the steam load, and specific heat load. So for a known portfolio of processes, this equation system can be used to prepare scenarios of cogeneration systems, as well as to detect the optimal steam turbine system that maximizes the power output for a given set of utility levels. However, when the turbine hardware model is used for the approximation of the power output in steam turbines that operate under extreme conditions, like the narrow expansion zones that are present into the dense grid of utility levels that is used for the biorefineries cases, then the turbine hardware model is quite possible to result some inaccurate approximations of the power output, while at the same time we need to face some non-linearities that are present into the expression of the specific heat load. So for this reason, we are presenting two alternative formulations, both for the estimation of the regression parameters as well as for the estimation as a quick estimation of the specific heat load. For the above reasons, where the literature expressions for the estimation of the A and B regression parameters are using only one operating parameter phi of the steam turbines, we reformulated the expression by using three different operating parameters, namely the inlet temperature of the saturated steam, the temperature difference of the steam, and the specific heat load. And we regressed again the experimental results, preparing a new regression model. For the estimation of the specific heat load, the following nonlinear system is used. However, in the case of the biorefineries, when none of the steam loads and the expansion zones and not even the processes are known beforehand, the challenges are more. So quite a common solution, common simplifications that is found into literature is the use of a constant specific heat load at the entrance of each expansion zone that relates to the very high pressure steam. In order to face with those simplifications and the nonlinearities, we are revisiting the expression for the estimation of the specific heat load by replacing the nonlinear term of power output to the steam load through the isentropic efficiency equation. So we are replacing this nonlinear term with the multiplication of isentropic efficiency times the isentropic enthalpy change. At next, we will have a better look to the turbine hardware model and the isentropic efficiency equation, then we can see similarities between these two terms. And in fact, the isentropic efficiency approximates the term 1 to b at very high steam loads. And as a result, we can replace this isentropic efficiency with this term. At the same time, we're using the same expression for the isentropic enthalpy change. And finally, by combining all these equations, we result to this equation, which on the right of this equation, the only unknown is the specific heat load of the previous step. And if we use for the first step the specific heat load of the very high pressure steam, which is already known, then we can make a better approximation for the specific heat load for all expansion zones. Finally, the proposed integration and cogeneration models are used in order to address a biorefinery value chain, which involves 31 candidate processes, for which you can find more information through our biomodeling platform. And the case here is to screen for promising biorefinery sites, and the problem has been solved twice, once to identify the biorefinery with maximum profitability and the one with minimum energy cost. The biorefinery site that maximizes profitability includes the production of xylitol, ethylene and resins, while the optimal turbine system includes 3 cylinders that result up to 13 megawatts of shaft work. The energy savings are estimated to 21%, while the maximum feasible profitability is estimated to 66 million euros per year. In the second case, we examined the biorefinery value chain to identify the site of minimum energy cost, and this site includes the production of xylitol, ethanol, sorbitol, and polyurethanes. Both the energy savings and the cogeneration in this case appear higher than those estimated in the previous solution, and especially energy savings are estimated up to 28%, cogeneration to 15 megawatts, and the minimum energy cost in this value chain is estimated to 10 million euros per year. The steam savings estimated in this solution are due to the indirect integration of the sorbitol production with the biomass fractionation process, while next the fractionation process offers 2.12 megawatts and 5.1 megawatts to all the production lines of the whole biorefinery. And as a result, the xylitol production line and the polyurethanes production line are working free of energy cost thanks to the heat provided by the fractionation process, while the ethanol production line saves up to 37% of its heat demands thanks to the heat provided by the fractionation process. Summarizing, in this work we have revisited the integration and cogeneration analysis, addressing processes as additional degrees of freedom in these problems. For this purpose, we have presenting a new representation, a new heat transshipment model that couples direct and indirect integration, while at the same time we have revised two formulations for the estimation of regression parameters and specific heat load for steam turbines. Finally, we have used the combined cross-interval transshipment with the turbine handling model into a biorefinery site in order to result in solutions with high energy savings and high cogeneration potential. Thank you very much for your attention.